Welcome to Continuing Education, Mastering Metrics, Harmless and Otherwise. It's great to be doing this again. Okay, so let me just give a little bit of a kind of a warm-up about the way we think about empirical work and applied econometrics. And I'm drawing here on material from my book with Steve Pischke. The idea is that there's a sort of essential mystery to the kind of choices and consequences that we study. And that's captured by this quote from one of my favorite TV shows, the Kung Fu TV show. Some of the older folks will have seen that in the original, and some of the younger may have seen, you know, Kung Fu Panda and Enter the Dragon and all this stuff that comes after that, and because of that. So the basic idea is there's a journey and there are paths and you make choices, and you know, you pick one thing or the other, and the econometrician aspires to know what happens at the end of the road not taken. So here is our grasshopper, and the grasshopper's making a choice, and oh look, if he goes this way, it's Y0, and that's what we'll learn. And if he goes this way, it's Y1. But of course, he'll only ever make this journey once and only see one of these. And yet somehow we're going to find a way to figure out what lies at the end of the road not taken. And we actually have a whole kind of machinery for that, and Alberto and Chris use the same machinery that I do to describe that. That's the language of potential outcomes. And the econometrician's job is to come up with a good research design. It might actually be an experiment, but it doesn't have to be a real experiment. It's sort of notionally an experiment to answer questions about the road not taken. A lot of the way we approach problems, and I would say from my point of view, this is the way I approach just about everything, is not only with poetry, but by asking questions. And the questions that I ask, I have in mind that there is an experiment that would answer those questions. So often I'll say in a seminar, what's the experiment you'd like to do? I thought I'd show you one of my favorite experiments, and you'll see why I like this so much. It's an experiment I had dreamed of doing for years. This is the experiment, an experiment that was done a few years back now, and was published in 2017 by my former student, Kyle Greenberg, who teaches at the U.S. Military Academy at West Point. And Kyle set out to study my prohibition on electronics in the classroom. So West Point, as many of you know, it's basically a selective college. It happens to train commissioned officers for the U.S. Armed Forces, but you know, it's just a college like any other, and they teach a lot of economics there. So they had a randomized trial where they took 50 classrooms that involved 726 students over a period of a few years. Now, West Point, unlike a lot of the colleges where we work, it has the kind of sensible default, I think, where the default at West Point is that electronics are forbidden. So nobody is allowed. And then, as an experimental matter, they decided to allow some electronics. So one of the treatment groups is allowed to use laptops and tablets, you know, promiscuously. Anything goes. And then there's another treatment group where you're allowed to use a tablet, but it has to be face up on your desk. The idea being that if the tablet is face up on your desk, you know, then you can't really check your Facebook page or something like that. The instructor will see. And then the control group is these three. So these are actually economics students. This is a randomized trial on the use of electronics in the classroom. And by working through this very quickly, it'll sort of set the tone. And also, it shows the way we look at quantitative numbers. We look at a lot of tables. So I want to just practice that very quickly. Okay, so the first thing I can show you, so here's a table with a lot of numbers. And maybe you can't see, but it's in your handout. So here's the control group. And here's some characteristics of the people. So these are means. So 17%, it's a mostly male group in the officer corps. White, 64%, 20-year-olds, they're freshmen. Some have prior military service. Many are athletes at West Point. And here's the high school GPA. And in the control group, here's the proportion who are using a computer. And they actually observed whether people use computers. And nobody in the control group uses computers. And then we have the key kind of contrast here. These are baseline characteristics. These are things that are measured in advance of the experiment. And then here's a comparison. So both treatments versus control. So let's just look very quickly at that just to refresh everybody on statistics. So what I'm saying in this column is, let's pick this row. Okay, here's the control group's GPA at baseline. The GPA is the high school GPA coming in, okay? And then this is the treatment control difference. So you can see it's a very small number. And then there's a number underneath it, okay? So let me just take, and the number underneath it is 0.04. So let me just take this opportunity to ask somebody what they think that number underneath it is. What do you think that number underneath that 0.04 is?
The t-stats?
It's not, but you're close. That was a good guess. That's also close. That's a good guess. What do you think it is?
0.04, that's a p-value?
She said that was wrong, so that's not a good guess.
Average amount?
What did you say?
Standard error.
It's the standard error, okay? A lot of the numbers that we look at in this room today, and hopefully in the rest of your lives, have this format. There's a set of means, and then you're comparing the means, okay? And then you want to have some measure of precision. You're going to make a decision about statistical significance on the basis of how much of that variance is, just sampling variance. Okay, and then for that purpose, you do compare the difference to its standard error. Somebody mentioned something like t-statistic. Was that you? You said that, right. So what would the t-statistic be?
Well, the standard is 0.04.
Right. What's the t-statistic for the hypothesis that the GPA is the same in the treatment and control groups? What's the t for that? Ballpark it. 0.25, which is very what? Not very significant, right? If it was significant, what would it be, Leslie?
Close to 0.
If it was significant, it would be close to 0?
No, I mean the standard.
The standard error would be smaller. The t-statistic would be bigger. How big would it have to be before you decide it's probably significant or maybe significant?
1.9.
Well, don't be about point. We don't need point. Two or 3 or something. Okay, economics is a one-digit science, as they say. Not even. On a good day, 1 digit. Okay, so that's the way we look at estimates. We don't take hypothesis testing too literally, but we do look at differences in means. And we do see something very useful here about a randomized trial, and this is kind of the purpose of the randomized trial. Okay, what is the kind of substantive conclusion from this table as far as the differences between the treatment and control group and their baseline characteristics? Salvador, what's the bottom line?
They're the same.
They're the same, okay? There's no difference between the treatment and control groups statistically in terms of their baseline characteristics coming in, so that's all why we did the experiment. We wanted it to be balanced, and it is balanced. So if there is a difference between the group that does and doesn't get electronics, it won't be because, by mistake or by design, you got better students in one group or the other. The random assignment made the groups comparable. Okay, well, let's look at the results. So let me just explain, what are the results? Well, you have to have an outcome. So the outcome here is a test score on your final exam in the Econ 101 course. Now, here's another thing that'll come up in a lot of my work. I do a lot of work on schools, and I use data on tests. And tests don't really have any natural units, okay? They don't mean anything intrinsic. It's not like, how far something is. That's sort of meaningful. I guess you could say a little bit arbitrary there too. But anyway, we standardize test scores, and the way we do that is we divide them by their standard deviations. So the outcome here is a final exam score in standard deviation units, and then this is a report on results where we regress that standardized test score, final exam multiple choice plus short answer, on a dummy for having been in the laptop class in a sample that pools the two groups. Now, with only that one dummy, it's just a treatment control difference, but we could control for stuff. So that's what's going on here as we move across the column. And across the columns, we're adding some controls like baseline GPA. We see that mostly doesn't matter. And anyway, the punchline is clear, okay? So the punchline is that the classroom, the treatment groups, and this particular version of the table pools the people who were allowed to use laptops with people who had the limited tablet. Okay, what's the punchline here, Vasiki? What emerges from this table as far as the treatment effect of electronics in the classroom for these students and yours?
The treatment effect would be significant.
It's significant. Okay, so that's certainly true, but that's not the only thing that's interesting. What else is interesting here, Denny?
It's not good to have laptops.
It's negative. It's a big, significant, large, negative number. Students who are allowed to use electronics have final exam scores that are 0.2 of a standard deviation lower than students who are not allowed to use electronics. And by the way, I didn't dwell on this, but it's important to know, the students who were allowed to use electronics did use electronics. Okay, so then we can see that here. Students who are allowed to use electronics, about 60% of them actually did use electronics. So the reason for this difference that I just showed you is probably that electronics use in the classroom reduces learning as far as we can measure it. How big is 0.2 sigma? 0.2 sigma is a lot. If you think maybe in terms of a standard normal distribution, 0.2 of a standard deviation is moving maybe almost 2 deciles near the mean. So that's a big reduction. Why is it statistically meaningful? Because the t-statistic here is on the order of 3. It's also very stable as we add controls. In fact, the students who had unrestricted laptop use have even more negative test scores, okay? So I love to begin my lectures with that experiment because it is a randomized trial and it justifies my rule about electronics, okay? So now you know that I'm not just saying that, it's based on science.